Yeah, let me start my presentation. I'm going to talk about these topics. Before going into the presentation, actually, yeah, I want to talk about, I'm quite getting nervous because, yeah, I didn't expect that much students can coming for my presentation, but it's a little bit nervous, but I'm also very happy to present my research topics to like very promising researchers in the future. So yeah, I hope my presentation give you any inspirations or any some clues or ideas for your research. Then yeah, I will start my presentation. And this is the general outline of my presentation, and I tried to do my self introduction, but yeah, Professor Sin already did that, so you can see here. And this QR code is for my personal website, but if you are guys interested in my research topics, then you can visit later. And as you can see, I'm affiliated in the Korean Army, and my rank is Major. It means I working for around 13 years for the Korean Army. And from my PhD study, I am quite passionate about some bridging some technology with national defense technologies. I try to working on those topics, and as you can see here, the Institute of Innovation for Future Army is located in the same building, the 7th floor, also in the basement floor. And also, our center is staffed by around 30 researchers, so has the graduate level researchers, including 8 PhD. And actually, our center is located in Gyeong, not in Daejeon, but we moved to here, Munji campus, for the better collaboration with the KAIST. So yeah, our task is basically we suggest or design for the future Army's visions, and also we try to do some defense R&D, research and development task using some technology planning. So yeah, I hope we can have more collaboration and co-works with you and other professors in the the KAIST. And then yeah, I try to get into my research topics. Before going to my I start with my research background. So my research field is air traffic management, and as you may know, or some of you are not familiar with this air traffic management system, but it is general systems including all the items, all the services, all the systems including aircraft or control towers, runways and airspace, everything included. And the first priority is safety, because this is a safety critical system, so some errors or incident can lead to any fatal accident. So first priority is the safety, but at the same time, the human operators like the air traffic controllers try to improve some efficiency so that they can accommodate much more aircraft in the limited airspace. As you can see, there are so many aircraft flying at the same time, and so as you can see, many aircraft landing and departing sequentially. And in this air traffic management system has some challenges. One of them is that the increasing traffic volume. So as you can see, in a very long term, the traffic volumes actually after the COVID-19, it restored the same level of the 2019, and then it keep going increase, and probably around 2050 it would be more than doubles traffic volumes. So it is quite important because our airspace is already saturated and it is already busy. So if we have much more traffic volumes, then it can lead to some issues. So I wanted to show some examples or some accidents. 2020 2024, in the Japan, there was some runway collision between the Japanese airline commercial aircraft with the Coast Guard aircraft. And the investigation revealed that there was some misinterpretation by some pilots. So the pilots in the Coast Guard aircraft, actually, they believe they already have the clearance to enter the runways, but actually it was not. So that's why Japan Airlines try to landing and approach and then collide with that aircraft. And another reason is that air traffic controllers actually failed to notice that this Coast Guard aircraft enter the runways. So there are some time to check it, but the air traffic controllers miss it, so it resulted in some fatal accident. It caused around 5 to 6 fatalities. And another accident is the more recent one, 2025. There is mid-air collision over the Potomac River between the U.S. Army helicopters and the commercial aircraft. And it is under investigate, but preliminary investigate shows that there was some miscommunication, the human errors, because the instruction, actually, air traffic controllers tried to give some instructions to the helicopter pilots, that is the path behind the aircraft, but it was missed due to some simultaneous microphone transmissions. And so that's why they collide in the air. And there is some factors. One is that this around the Washington airport is already quite complex, and there was several near-miss incidents already. So they can be they can take some measures to resolve these problems, but it wasn't. So it resulted in some very fatal accident here. So recent statistics shows that there was still some aviation crashes in even 2025. So safety concerns come from these complex operations in the busy airspace. And the other challenge is the new concept of operation, that is the advanced air mobility or urban air mobility proposed by some NASA or FAA in the US. And this concept, as you can see here, many drones and UAVs or air taxis can be incorporated or integrated into the conventional our airspace. So these characteristics are quite different from the commercial aircraft. So this is not non-cooperative, especially the air traffic control management system is centralized and the human in the loop systems, but these drones can be included around more than 1,000 number of the drones in the busy airspace. And in order to incorporate this new concept of ideas, the NASA tried to propose new concept of the traffic management, including all the operations, the conventional air traffic control, and also the new concept of operations, which means the low altitude, including some drones and air taxis, and from the high altitude, including all the aircraft, even in the high altitude. So this integration of airspace could give us much more challenges because the operation types can be changed, because it can be more semi-autonomous system, and also it requires the low altitude operation requires some distributed and scalable operations, because there are more than thousands of drones or UAVs can be come into around urban areas. So these challenges proposed by some increasing the air traffic demands or traffic volumes and new concept of the operations into the current conventional airspace, then we consider both operations. As you can see here, the high altitude operations and the low altitude operations. But for that, we still require the human monitoring and the intervention, even we consider some distributed operations, because it is safety critical problem. So we cannot exclude human decisions from our systems. But we still have some better improved traffic management to cover quite large number of the drones or UAVs operations. So in order to help or assist these human operators, it requires this intelligent decision support system for this integrated airspace operations from low altitude to high altitude here. So we can take some machine learning or big data analytics approaches for this, and especially the timely kind of real time or the interpretable, because typically machine learning, like the neural network, has no, we cannot exactly extract some reasoning process or how do they make the decision. So we have some interpretability for human decision, to assist the human decision making. So we require this kind of decision supporting systems to enhance the situational awareness of the human operators, and also at the same time, we also assist their informed decision making for such as conflict detection and resolution, or the scheduling or sequencing problems. So in order to develop this kind of decision supporting systems, I try to have three research directions. As you can see here, from big data analytics to the multi-agent system, and this can be used to develop these decision supporting systems. And as you may know, the big data analytics can have some capability to collect and processing the huge number of data, even the real-time streaming data. And big data analytics is basically data-driven method. So I found or observed some limitation of data-driven method. I tried to incorporate the physics-based method too. So physics-guided machine learning tried to more properly incorporate both methods to leverage the strengths of each method, and then move on to the multi-agent system for model the entire complex systems and some interactions between the multi-agent aircraft or other things. And a fourth approach is the big data analytics, basically the data-driven method. And this method can be divided into 4 different analytics. As you can see, it shows each analytics try to answer each questions, and it requires different level of the human inputs to reach the decisions or actions. And from here to here, they has the different purpose, but it try to identify some new things from the data, try to find patterns, or they try to give some advisory for some human operators. And one thing I want to mention here is that for the decision support system, the prescript analytics is important, but other analytics is also important. And here is a summary of my research works. And as you can see, the 4 different types of analytics are interconnected, and especially the descriptive analytics try to identify or mine some patterns. For example, this work is trajectory pattern identification and classification work, and it is used for other diagnostics and predictive or prescriptive works or analytics, because for this work, from the huge number of the trajectories, we can grouping some specific trajectory patterns, a finite number of patterns. Then we more focus on specific patterns for the next task. So for example, if we, it's kind of the clustering. So if we find some patterns, then we can divide some specific trajectory patterns, and we can focus on some specific pattern for anomaly detections or trajectory predictions. Then we can have better performance, or it can be effective and also it can be efficient because we take the small number of data than actually it was. So similarly, the trajectory prediction is used for other prescriptive analytics because it can extract the future information based on the observed trajectories. Then based on the future trajectories, we can decide which actions or advisory is better compared to the multiple alternative options. So in this regard, in terms of, in order to develop this kind of decision support systems, only prescriptive analytics is not used. Although analytics can be combined and interact for the much better the efficiency and the effectiveness. And in this presentation, I focus on two topics. One is the trajectory prediction, and the other is ETA prediction and arrival sequencing problems. And the first topic is physics-guided trajectory prediction and generations. And yeah, let's get into the details. So I believe you guys quite familiar with this trajectory prediction. So trajectory prediction is try to extract or predict the future state of the aircraft. And it is widely used in the air traffic controller tasks such as this kind of things to ensure some safety and efficiency. And this trajectory prediction can be divided into two different methods. One is the physics-based one, and the other is the data-driven method. And physics-based method, as you can see, we have some specific mathematical models or aircraft dynamics model. Then from that, we can propagate the future state. On the other hand, data-driven method typically has no specific model, but from the collected data, the model is trained directly to learn the trajectories, and they can provide the future trajectories. But as you can see here, from these four types of metrics, each method has the advantages and disadvantages. So physics-based methods are better interpretability and feasibility compared to the data-driven method, but at the same time, the data-driven method instead better complexity understanding and better future predictability of the trajectory prediction. So in this situations, the ideal case is we only use the strengths of each method. So in order to achieve those goals, I try to incorporate the two different approaches. So here is my initial work to incorporate these data-driven predictions and the physics-based prediction. And it is basically initialized by taking the observed track point up to the current time step. And the data-driven prediction then generate the one-step ahead prediction, and which is used as the pseudo measurement for the physics-based prediction. And in this work, I use the Gaussian mixture model that can learn some expected future behavior for the one-step ahead predictions. And firstly, the trajectories can be we can partition the trajectories into this past trajectories and future trajectories. And by the model is trained by some data, so we can have the prior mean, mu, k, the multiple components of the Gaussian mixture model. And then based on these equations, in order to predict the future information, we condition the future distributions on the observed trajectories like this. So as you can see, based on these observed trajectories, we can calculate this posterior means. Then the weighted sum of this mean can result in the predicted state of the aircraft. And then this one step ahead prediction can be fed into these physics-based predictions. Actually, this estimation algorithm can take the measurement, but we call it the pseudo measurement because it is not actual the measurement. So, but actually it is working like the measurement in this physics-based prediction. So that's why it is called the pseudo measurement here. And physics-based prediction take this pseudo measurement, and then based on this hybrid estimation algorithm, we can account for the aircraft dynamics here. So we chose this residual mean interacting the multiple model that is quite explain some maneuver uncertainty very well using some multiple maneuver mode. So here is some details. So this hybrid estimation is actually modeled as this stochastic linear hybrid system, which has the continuous dynamics and also at the same time it has the discrete dynamics. And in this work, we consider only two maneuvers, that is the constant velocity mode and the coordinate term mode. And if given some measurement, we can estimate the current state accurately. And here is the general structure of the algorithm, and here is the example. So if we have the current position, then we are here. Then based on our aircraft dynamics, we can propagate into the here is the measurement. We can propagate to the future. So since we have two different maneuver modes, we can have two different prior estimates, and we have two different Kalman filters for each mode. And by finding some minimum mean squared error estimate between the measurement and each mode estimate, prior estimate, then we can have two different posterior estimates. And from here, we can compute the mode probability based on Bayesian rule. Then based on this mode probability, we can finally get these estimations which can account for dynamics. So this dynamics can correct this measurement based on the aircraft dynamics so that it can result in more accurate estimation of the state. So here, from this process, we can get one step ahead prediction finally. And this is the trajectory prediction, and it can be further predicted. So the one step ahead prediction can be going back to the data-driven predictions, and this process done iteratively until some predefined these prediction horizons. So why this hybrid modeling is important, I want to show some illustrative examples. So the red one is the data-driven method, and as you can see, the current trajectories, we are here at this time step, and as you can see, the aircraft going straight, which means the probability of constant velocity mode is 0.99. So which means it stay on the constant velocity mode, but suddenly the Gaussian mixture model generates somewhat infeasible the predictions, as you can see here. So this is the vector of the current time step, and the prediction shows somewhat infeasible or some unexpected maneuvers here. So this is not match the current dynamics. So here, the pseudo measurement from GMM has been corrected by dynamics, which means by by the physics-based method, then it going back to the actual trajectories going. So it get close to the actual trajectories, then it can improve the more accuracy. And here is some comparison result between the data-driven method, the GMM, and the LSTM, long short-term memories for the arrival trajectories, and here departure trajectories. And note that the LSTM shows the better performance compared to the GMM because it is some small setting issue that LSTM is do the one step ahead predictions iteratively. However, the GMM generate full future trajectory at once. But since then, the LSTM accumulate the errors step by step. So that's why this result much worse than the GMM. And anyhow, in this example, as you can see here, the hybrid method outperforms the other data-driven method. And this work can be extended to the much better the machine learning model, because previous work I focused on some conventional machine learning models, but for this trajectory generation task, I tried to adopt this BERT model from the transformers. So, and also I tried to enhance some interpretability by incorporating the physics guidance. So this physics guidance extracted from the hybrid estimation. And as you can see here, this is the mode probability. There are 3 different modes, and this shows the rate of turn. And here, initially it goes the constant velocity mode, and then coordinate turn, and going back to the constant velocity. And as you can see, these values are continuous state, but for the machine learning or the artificial intelligence training, this kind of continuous state is not that much helpful, because if we have a large data set, then the machine learning models can understand this continuous state. But if the data set is limited, then this continuous state hamper or deteriorate some performance of the model. So that's why here I discretize these values to the just mode informations and simplify the rate of turns. And it resulted in obviously better performance for the models. And this BERT model actually utilized the attention mechanism. You guys may know this attention mechanism. This is the core part of this BERT model. And it is really useful to handle time series trajectory data. And then we can have the question, so what is attention? So this attention is basically coming from the humans. So rather than interpreting or taking every information one by one, we can, or humans can typically pay attention to some specific important part of information. So here is some examples. If we have the self-driving car or autonomous car, then it wanted to know, it wanted to determine if it is okay to cross the intersections. Then typically humans check the traffic light or the pedestrian on the crosswalk. So here, the attention mechanism exactly working like the human attentions using the weight here. So this is the simple example. So input can be some section of the images. Then output would be yes or no to these questions. Then attention mechanism try to learn which inputs are more relevant or more important. Then they can give a higher weight for that specific informations or inputs. And here we can focus on 6 image sections. Then the weight can be given by this attention mechanism. Then the higher weight means that more importance for this to make up the decisions or the outputs. So it can be expressed by some weighted sum of these functions. Then finally we can get output of like this. So using this weight, this attention mechanism can mimic the human attentions. It can efficiently working by attending some specific important part of inputs. And the widely used attention mechanism is the self-attention. And from the input sequence, we typically extract 3 different vectors, query, key, and values. And query is like some questions about which data point or track point is important. Like in the previous example, do you see the red light in the traffic signal like that? And then the key is the answer to those questions. So it may yes or no, or even maybe. And the values are combined with these query and key pairs. It makes up the outputs. And the self-attention mechanism is well known because it shows the efficient computations, because it can be do the matrix can be expressed the matrix form, because if the query and key and values are extracted, then those values are deterministic, then we can take the parallel computation using this matrix form, and we can compute this attention. And it is also called, also known as this scale dot product attention. And this parallel computations is useful to train the models because we can take advantage of multi-cores or a computation source. And this can be extended to the multi-head attention, because this attention allows to the model to learn much different types of representations or some dependency within the input sequence. So this, based on this multi-head attention, it can understand the trajectories, time series trajectories. And here, I also incorporate some physics informations, directly learn physics using these physics loss functions, because as you can see, this mode information given as an input, that is the green, but output was quite different from the given physics guidance. So in order to reduce this discrepancy, I try to use these loss functions, that is the soft constraint in the loss functions. And then finally, we can fed or input some multiple different types of physics guidance to generate multiple trajectories iteratively. And this is the general framework. And in order to evaluate this work, I try to set up the experiment, and I compare with the standard BERT with the physics guided BERT, and both have the same number of the trainable parameters. And here is the data set in the some in-route sectors. And here is the evaluation. So in terms of this mean absolute errors, the performance is somewhat comparable. But in terms of this root mean square errors and the standard deviations, the physics guided BERT shows the better performance, because thanks to some physics guidance, it can have some physics informations. So in this case, these trajectories are not widely observed patterns. So it is the rarely observed in the training data set. So in this case, by combining the physics information, it shows the better prediction performance. And there is the other metrics, completeness, because in this example, we try to generate the trajectories to arrive the end of the sectors, the black boundaries, and we want to check if the generated trajectory is actually arriving around the boundaries. And this success rate, as shown here, and yeah, the physics guided one shows the better. And lastly, in terms of physics conformance, as you can see, without the loss, physics loss, it shows much spiky and frequent change of the mode. But with this physics loss, it shows the better performance in terms of this mode profiles. So in this regard, by combining this physics informations or physics data into the data-driven method, it can improve some performance in terms of this trajectory generation. And if we can provide multiple different some physics guidance, then it can generate different types of trajectories iteratively. And as you can see here, the color-coded trajectory shows some different travel times. So blue one is shorter travel times, and red one shows the longer travel times. So it shows some diverse trajectory generation, and it can be used for the dynamics case. So if the aircraft encounters some sudden situations, they can generate some multiple trajectories and then choose one of them to avoid some adverse weathers here, or to complete resolution, it can choose one of the other the conflicted trajectories here. And yeah, this is for the trajectory prediction and generation part. And yeah, from this work, we can learn that by combining some physics models can assist the performance of the data-driven method. And there are many different types of methods to incorporate some physics information, and I try to use some direct integration, and at the same time, I also try to use the soft constraint method. And the next topic is multi-agent ETA prediction and arrival sequencing part. It is related to some multi-agent system, which is one of my research directions. And for the multi-agent system can be used for this decision support. And I try to use this multi-agent system for this realistic landing sequence, which means actually it is not optimal landing sequence, but it is considers some practical considerations by the air traffic controllers, and also at the same time it can provide the arrival times. Here is the research background. So as you can see here, the existing approach shows that the ETA prediction model predict ETA for each aircraft, and once those ETAs are collected, then state information are incorporated into the sequencing optimization, and then it gets some optimal landing sequence here, and based on that, the air traffic controllers take an action for the control. But in the previous research shows that the air traffic control is really matter, which means that, as you can see here, it shows some influential factors in some flight delay predictions. And as you can see, they test by excluding one of the factors among all the input factors. And as you can see, when we exclude air traffic control factors, then it results in highest increase in mean squared errors. So in this regard, air traffic control can be incorporated into the multi-agent systems based on by capturing some interaction between the multi-agent, multi-aircraft or multi-agent. So in this regard, the multi-agent, one single model can provide, take all the trajectories at once, and they try to emulate the air traffic controllers from the past operations recorded in the historical data set. So historical data set has the past operations, and the past air traffic controller's decisions. So this multi-agent model can understand the traffic scene and their interaction so they can emulate the air traffic controllers, especially for the arrival sequencing. So these predictions or the outputs can be decision inferred predictions. So in this regard, I try to use this multi-agent system. And one issue is that actually in the attention mechanism or any neural network previously doesn't consider this multi-agent system. Then that is the issue, because in the input sequence, if we have this multiple aircraft and time series trajectories, then in the input sequence, all the trajectories from all the agent are concatenated into one dimension, which means this time and social dimensions in this scene was removed. This means that the time, temporal information and social information, that is the agent identity information, because the blue aircraft in the neural network, conventional neural network, they didn't notice which input sequence or portion is belong to which aircraft. So in order to preserve or maintain this agent information in the neural network, we can use this agent-aware attentions. And this attention have two separate queries and keys. The previously mentioned that it used the separate the layers. And the first layers focus on the attention to the same agent. The blue one focus on or attend to itself, red one, and the yellow one attend to itself using this masking matrix. And at the other layers, using these operations, we can focus on the agent attend to the other agent, not the ego agent. They attend to the other agent using these operations. And these two separated layers finally are merged into the one for the attention weight. And then we can finally get the attention weight like this. And so using this this agent-aware attention, they can preserve their agent information. They can differentiation the agent. So they can, in this one-dimension sequence, they notice some sequence coming from some red or yellow one, or they can understand some time steps. So here, this agent-aware attention try to keep or maintain some agent informations, and also here time encoder try to incorporate or encode some time steps to the input sequence. In this regard, the proposed neural network can maintain the temporal and social dimension informations. And here, as you can see, this is the attention weight for the multiple aircraft. And as you can see, ego agent weight level and the other agent weight levels are quite different, which means that typically in terms of this aircraft, it more focused on itself based on this ego agent, the bar, and it also focus on other agents too, but in terms of these interactions, it more focus on the neighboring aircraft, as you can see here, like that. And in these examples, it more attend to this already approach phase aircraft. So this means this aircraft try to land after this aircraft. So by using this attention weight, we can understand the weight, or in order to make up some outputs, which predictions are originate from which weight, like this. And also, for this arrival sequencing, one of the constraints is that the separation between the leading and the following aircraft. So once, only if they violate this specific the separation time, then it gives some loss values during this backpropagation. That is the training process. And in order to test this proposed algorithm, we use this surveillance data set. And this ADS-B data typically has 7 features, and I also included these wake turbulence categories for the arrival sequencing. And one issue is that it looks good, but actually it has some irregular sampling rate, range from some 20 to 60 seconds. So in order to address these issues, we take some reconstruction of all the trajectories like this, so that it can have some regular sampling rates based on some regularized least scarce optimizations. And as you can see, much smoother and much regular sampling rate, around 1 second. And based on this pre-processing, we do some ETA prediction performance evaluation. And as you can see, this is the comparison result, and this is the conventional gradient boosting machines and the transformer. These two are single agent model, and these two are multi-agent model. And in terms of the ETA prediction, the mean absolute error and root mean absolute error, 2 different data sets, it shows the better performance. And also in terms of the separations and the average violation time, proposed method still shows the better performance in terms of these ETA predictions. And it can be moved on to the arrival sequencing evaluations. And this is actually compared with the conventional optimization-based algorithm. And this arrival sequencing, we have one specific metric, that is the sequencing similarity to the actual air traffic controller's decision. So here we use these 2 different length correlation coefficients to measure how much each sequence are similar to the actual one. So these 2 are length coefficient metrics, and here is the result. So we establish 3 different conventional sequencing algorithms. And as expected, in terms of the efficiency, the proposed method shows not that good performance, but it is similar to the receding horizon control method. But in terms of this sequencing similarity, that is how much it resembles to the actual air traffic controller's decisions, then it shows much better or much similar to the actual one. And in terms of response time, this is the multi-agent system. It can provide just at once, so it shows the better computation efficiency. And although I want to say that although the proposed method shows some just normal performance in terms of this efficiency, but this work is meaningful. I want to show some illustrative examples here. And here is the 5 aircraft tried to landing at the airport. And one of airport, the receding horizon control and constraint position shifting algorithm generate the optimized arrival sequence, and it requires this aircraft to land in 3 minutes. But however, as you can see here, proposed method and actual one is much slower than that. This is because if we focus on this aircraft based on this travel time distributions, actually within 3 minute landing is practically infeasible. It is not impossible, but it is not user for these landing procedures. So which means this optimization algorithm can provide some unrealistic arrival sequence. So this can be caused by some large prediction errors in ETA predictions, and also some predetermined the time window in the sequencing algorithm. So combine these two, generate this kind of this unrealistic arrival sequencing. And also, this proposed model is actually evaluated by the subject matter experts, that is actually the air traffic controllers, and by 4 different air traffic controllers prepare our proposed method sequence. As you can see here, our model is more frequently chosen by the air traffic controllers, and they provide some consideration for their decisions. And as you can see here, they consider some practicality of this sequence. So they consider some their own preference, but they also consider some air traffic control clarity and control complexity, because there are multiple aircraft from up to 20 or 30 aircraft try to land at once. So in this regard, the air traffic control is quite important and account for 43% of the total for this arrival sequencing. And also the feasibility is also account for 14%. That is the previous case study. So this work shows that emulating the air traffic controllers can result in some slight degradation in performance, but instead it leads to some smoother operation with some much safety margin. So they can have some buffer to handle if there is some emergency or unexpected situations. And here is some dynamic cases. So multiple aircraft comes in, some aircraft landing, and new aircraft keep incoming to the airspace. Then the ETA prediction and arrival sequencing is exactly same to the actual decision by air traffic controllers. And yeah, this is for my presentation, and this is the summary. And in order to develop the decision supporting system, first try to focus on better predictability, and also feasibility from the physics-based method. And in this work, we also account for some practicality, because we are in the human-centric systems. So practicality is very important for the air traffic control, and also attention mechanism. Using the attention weight, we can have better interpretability for the decision makings. And yeah, this is for my presentation. And if you guys have any questions, just feel free to ask.
No question? At least clear. So I'll start.
Yeah.
So in the first part of your presentation, you mentioned about how you can improve sort of performance using physics. But there are so many different ways you can use physics to improve data-driven approaches. And you have used 2 approaches, if I'm not mistaken. One is the first process, this one is creating pseudo measurement of
Mhm.
physics.
Mhm.
Secondly, is you incorporated physics into loss function.
Mhm.
And you directly actually obtain your train your network.
Mhm.
But there are some other ways I think you can use.
Mhm.
Which one is better you think? Because there are so many different ways. I
Mm.
don't really know which one is better because of what. And so do you
Yeah.
have any idea how
Mhm.
you can try? What are the other methods you can use and so on?
Yeah. Firstly, thank you for very good questions. And actually, I couldn't say which one is better compared to others, but it depends on some domains. Which domain is quite domain-specific problems. So that's why I try to use multiple some options for to incorporate these physics models. But in terms of these air traffic control problems, I can just use stack two different models was working well. And actually, the next work is not trajectory prediction, but it trajectory generation. And it is along with some physics guidance that is human readable some profiles so that the operators can generate some multiple trajectories more easily and also incorporate some physics laws together. But in both problems, I take several metrics, but it is quite domain and data specific. So in these problems, actually, the our data set is ADSB data, and actually we don't have the control inputs for that. So we only focus on the estimations. And since we have only the estimated values, or estimation algorithm can be used for this physics model, so is the best way I can choose. But there is another options such as the physics-informed neural network directly solve some partial differential equations. So if we have some control inputs, I will try to use those things. So if I have some data set for the drones, I can do that. But for these problems, I can use those options. So that's why I focus on some limited approaches. So I think it's not a good answer, but it is generally speaking, it is depend on some domain.
Thank you. In the first example, in the first part, where you predicted trajectory and compared the performance of it, because there's way other like approaches like LSTM and GNN approach. Compared to the like very conventional physics-based approach, how does compare?
Actually, previously I used the physics-only method. That is just simply propagate the current state into the futures. Then uncertainty going crazy, going bigger and bigger, and especially it depends on the current the mode or maneuver mode. So if currently it take the constant velocity mode, then in the future state is still the constant velocity mode, which means they cannot account for the better predictability in the futures. So that's why I didn't consider the physics only model in this
So
case.
they still use INN.
Mm-hmm. Yeah.
So if you have different types of like maneuver modes, we don't just use,
Mm-hmm.
we have to use like MM or interactive MM
Uh-huh.
or like continuous MM type of like approach. So compared to this kind of approach,
Mm-hmm.
I think it's working okay. How is it, what is the main difference between like proposed approach where you get the pseudo measurements?
Mm-hmm.
I don't really get what is actually exactly the pseudo measurement. seems like you said, one time step prediction on something, I guess it's a maybe trajectory.
Yeah, trick.
Compared with MM type of approach, we have a lot of different types of MM.
I am, yes.
How does it compare? Because I thought MM approach will work very well in this kind of situation.
I'm not sure I understand your question is correctly. So your question is, I can use some other version of the IMM, yes, for these cases? Or you mean just IMM only for these trajectory predictions? Or?
Yeah, I think if we use some type of IMM, then if you have two modes. You have like constant kind of mode, constant turning,
Yeah.
and then again constant, I guess, close. So if we use like IMM approach, we predict the approach. It still works, isn't it?
Yes, actually in the existing works using this IMM actually requires some flight paths or a flight plan to correct those maneuver mode, or even our model can have multiple mode, even 3 or 4. But if we don't have some specific information for the futures, it just propagation into the current mode. So in this means the previous works, the physics-based predictions try to incorporate some priori of some future plans. So if we have those plans, then we can just use the physics-based predictions. But if we don't have those information, then we cannot do that. And especially in this case, around the airport, the operation is really complex, and air traffic controllers gives quite frequently some radar vectors. So they have no specific flight plans. They just directly give some instructions, just go straight or turn like that to make some required delays. So without that, we cannot use the physics-based only model. So that's why I try to use the hybrid modeling of two methods.
So for the multiple estimated time variable problems, how does it scale? So you compare the performance in terms of the computational cost, depending on the situation where you might have quite a lot of aircraft flying together. How does it scale? If you increase the number, computation is becoming heavier, much more heavier.
Yes, typically in the terminal airspace, they're typically from one aircraft to the maximum is 25 to 30 aircraft, and in the data set they include all the data set, and this is the average response time. So yeah, it can cover around 30. But yeah, I think if we can increase some number of the aircraft, it still works.
So it's a millisecond.
Yeah.
I mean, for the training.
For the training.
Yes.
Yes. Actually, for the training, the data set is just 6 months data, and it is around, I think, more than 20,000 trajectories. Traffic scenes with the multiple trajectories, and actually for the initial model, it takes 1 day to training in the core app. So using some GPU. So if we have some, so that's why it is somewhat not that big neural network. The structures just the encoder is just 3, and if we have much more data, then training time increases. Also, the required model requires some the fine tuning, the structures and number of multi-head attentions and those things. And
So, in terms of the performance, you mentioned the performance is not like it's comparable, but it's not the best. But it's providing much smoother trajectories, which ATC controllers actually preference.
yeah.
Why is it providing smoother? What is the kind of the reason this is providing smoother trajectories?
Yeah, I think I briefly talk about this. So actually, they try to have some buffer, which means if they actually know the optimized sequence, they have the some manager system, so they can have some optimized sequence, but they just didn't follow those sequence because they try to have some safety margin because there could be some wind gust or other some adversary weather. So and also there are some times to communicate with the pilots, communication response time. So they try to have some time or some buffers they can control those aircraft. So they didn't just follow the optimized sequence, but they have their own practical considerations when they have some traffic scenes.
So here you have the ETA estimation, and also you have the optimal sequencing. Right? When you get the optimal sequencing, how did you get the optimal sequencing? So that's the how do you get? So how do you get the optimal?
I mean, yeah, this arrival sequencing just coming from the output, the arrival times, and just sorting that, then that would be the sequence. Thank you.
먼저 원장님 말씀 잘 들었습니다. 제가 질문할 게 총 두 가지가 있는데 트레이토리 프리딕션 관해서 질문을 드리고 첫 번째는 데이터 드라이브 프리딕션을 사용하고 PX 프리딕션을 사용하지 않습니다. 근데 결국 최종적으로 아웃풋으로 평균과 분산이 나오게 되는 그러면은 데이터 드라이브 프리딕션에서
네.
그 주변 환경까지를 고려해서 어떤 안전과 안전성을 고려해서 프리딕션을 하는 건지 아니면 그냥 그 상태 방정식에 의해서 아웃풋을 내는 건지가 궁금합니다. 두 번째는 현재 데이터 드라이브 프리딕션을 보면 뭔가 트랜스포머라든지 어떤 거대한 신용망을 사용하고 제 생각에는 결국에 제어까지 수행하기 위해서는 모델이 너무 커지면 그 제어주기 가장 도닥지 않습니다.
네.
그래서 그 모델을 좀 최소화하기 위한 어떤 연구를 있는지
네. Should I answer in English or just Korean?
It's okay either.
Yeah. So first question is that that is the output of this data-driven prediction is actually just it can have the state and also covariance of these states, and actually for the this based prediction, both are incorporated into that, and actually it considers some uncertainty in terms of this covariance, but they didn't consider specific safety concerns for the predictions here. And is that the question, right?
그 두 번째는
네.
데이터 드라이브 프리딕션의 모델을 주의력 연구가 있는지
For the second topics?
저 데이터 드라이브 프리딕션의 모델 크기가 커버리면 그 처리하는 여건도 늘어날 거죠. 그에 따라서 저희가 지어주기를 길게 설정해야 되지 않습니까?
네.
반면에 트랜스포머 말고 좀 더 그 작은 크기의 모델을 사용하는 이유가 있으십니까?
Yes, obviously there are so many models for all the some applications. So as you said, there are some more efficient model. One of them is previously I showed the gradient boosting machines. That is really efficient model. But although I still stick to this transformer variant, is that it can understand some complex the traffic scenes, because there are so many some features or factors to some lead to the outputs. I mean, so there are so many complexities of the operations. So in order to cover those models or the operations, and we have no choice but stick to the large models for that. But if data set is small, then we can use some efficient model. But the trajectory data actually it keep accumulated. So it is, I believe it has already around 10 years of the trajectory data, but I just used the 1 year's data or 6 months data. So if we take all the trajectories, then we require much bigger models. Is it?
Any other questions? Just have one more question.
Yeah.
So most of the students are not like studying like aircraft
Mhm.
space engineering. So they are mainly doing ground mobility. Excels, I think my bad. So if we, assuming that we might use trajectory prediction, which is quite important for also ground mobility,
Mhm.
you think what kind of things we might need to consider, we are considering to use your approach or propose approach? Are there any things they might need to consider more, or maybe something different? Because in my opinion, in the ground mobility, in order to predict the trajectories of the other vehicle, which has no kind of like intention given to us,
Mhm.
it's very difficult, maybe different problems, because the mode is quite different depending on their intention.
Yeah.
So do you have any suggestions, what kind of things we can further consider or study as a research?
Yeah, I believe, I don't much know about some ground mobility, but since if I focus on this kind of data-driven method, the trajectory prediction is quite general in this domain. So this can be applicable to the ground mobility or even air mobility, whatever. But the one thing is that typically the AI or machine learning domains focus on some efficiency and the performance of the models. They just have the same data set. They use the different types of models, and they shows very small increase of the performance. But for the ground mobility, they requires some sensor fusion using some LiDARs or other 4D radar. They use some kind of multiple video data, whatever. Those are need to be combined. And at the same time, we need to consider the real world operations or the maneuvers. Actually, for the ground vehicles, we don't know as the professor Sin said, we don't know the intention of other aircraft or other vehicles or even the pedestrians. Then we can incorporate the intent inference. So one of the research field is the intent inference. If we have some intent of the other around the traffic scenes or some situation, then we can have better predictions or better decision supporting systems. And also there are some other research regarding some context-aware algorithm. That is, they try to understand the self-attention algorithm, try to focus on some specific part, but we also need to check around our situations. We are on the highway or we are on the just small road. We need to check or we need to know those differences. So we can incorporate those some practical considerations or some contextual informations too.
Yeah. To me, maybe it's in like air traffic management too. What is quite important is the case, which is not very common.
Mm-hmm.
So, for example, if we can use the data to predict, it means actually we see a lot of data, or we see a lot of patterns in the data. But what is quite challenging is like something we haven't seen as common, and which is like posing a great kind of threat to us.
Mm-hmm.
So in the ground mobility, that's kind of edge cases are quite important. How do you predict, or how are you able to predict this kind of edge cases becomes quite important.
Mm-hmm.
Even I think in air traffic management is quite important too, because we start to actually incorporate the AAM,
Mm-hmm.
where we haven't seen yet. Therefore, I was wondering how can we actually improve this kind of like prediction, training prediction, either using data-driven or physics-based like prediction. You know, especially in the data-driven approach, how do we actually like handle
Mm-hmm.
this kind of like very sparse data cases?
I'm not sure, but one suggestion is that I believe you may know the transfer learning or the future learning. So we can have the other domains, data-driven models, if the other domain have enough number of data set, and we can have the trained model by those data, then we can transfer those models to the unknown or quietly scarce data set is only available. Then we can do some transfer learning or the future learning to transfer this model to adapt to the new domains. So if we have some limited number of data, then we can have the similar operations, such as if we try to transfer to the AAM, then we can operation of some helicopters or some quadcopters. If it's already recorded in the data set, then we can have the model of that. And then if we have actual some very small number of the AM data, then we can transfer to the domain. And then we can have that model. And if the data is accumulated, then this model is learning online, and then it model is getting better and better. Yeah.
Okay, great. Thank you very much.
Mm-hmm.
One other question, I guess. Then let's give big hands to you.
Thank you so much.